a view plane as an example. This is one view plane of an example which consists of 2 points, P1 as well as P2. That is, this is actually the projection of P1 as well as P2, which is been lying on this person. These 2 points, how projection is, you can check out the projections with respect to point 1 as well as point 2. Both are parallel with respect to each other. Actually, both the projections with respect to the points will be parallel in any of the direction in some particular plane. So that is how parallel projection seems to be. Basically, as I told, the z coordinate will be discarded. Parallel projection discards z coordinates and parallel lines from each vertex with respect to the object, depending on the intersection of the view plane. That is, it will be performing the operation only in both the plane, that is xy plane, but the coordinate with respect to z, if it consists of z coordinate, it will discard that kind of coordinate there. In this kind of projection, basically direction of projection is being specified. That is, if you can check out here, this from this point, this is the direction, right? I can tell it is moving towards the right of the point. Okay, so that kind of projection is being displayed here. That is, in parallel projection, specification of direction of projection instead of center of projection is done. That is, basically you specify the direction of projection, not the center of projection. That is, if as we know, a plane projection can be done. With respect to parallel projection, the direction of projection is specified, but not whatever the center of that particular projection is there, it is not displayed with respect to parallel projection. Then what happens with respect to parallel projection is, it basically preserves relative proportions of the object. That is, equal proportion of the object is being done with respect to parallel projection. That is a kind of view. If you take an example of a monument here, if I take this as a monument, if you want to project this angle with respect to the front view of the angle in the view plane, you can do this with respect to lines are actually parallelly displayed onto the view plane. That is, the projections are parallelly displayed into the view plane. There is an example of parallel projection. It is used in computer-aided drafting as well as design to produce scale drawings of 3D objects. That is, the example you can give your CAD as an example of parallel projections. If you want to draw a pyramid with respect to CAD, what do you do? Basically, the technology used behind that is parallel projection itself, where you draw an 3D object with respect to the software kind. Then there is, as I told, there is a taxonomy related with respect to parallel projection. So this is the taxonomy. If you consider parallel projection, the first division of the parallel projection is orthographic projection, where orthogonal dimensions are being performed with respect to that projection. Then what are the parameters with respect to orthographic projections? That is top view, front view, side view, as well as the isometric view. This basically tells the kind of object we'll be using in that kind of projection. So this is the flow or the types of views with respect to parallel projection. Then, as I told, parallel projection, it consists of a type, that is orthogonal projection. What comes under orthogonal projection? Basically, it is the direction of projection which is normal to the projection of the plane. That is, as I told, if you want to display the front view of a particular object, we'll be using parallel projections, where the lines which are projecting that original objects are parallel to each other. Similarly, I can represent orthogonal projections as the direction which basically gives the direction for projecting that kind of plane. There we have three kinds of orthographic projections. One is front projection, top projection, as well as type projection. This basically tells you the kind of phase you are projecting of that particular object. And you can check out, this is an example of orthogonal projection, where it is basically, as I told, orthogonal projection is basically used to evaluate or find out the front view, side view, or the back view of that particular object. With respect to this diagram, I can tell if this is an original object, the front view of an object is just a square here, and the side view of an object is just similar to that of a folder shape, right? The top view, that is, it consists of a plane view. So check out the points related to the diagram. Orthogonal projections are most oftenly used to produce the front, side, as well as top view of an object. As I told you, front, side, as well as rear orthogonal projections of an object are called evaluations, and the top orthogonal projection is called plane view. That is, if you are finding out the front view as well as side view of that particular object given to you with respect to orthogonal projections, I can tell those are the evaluations you are doing with respect to the object. If I tell to find out the top view of an object with the help of orthogonal projection, I should call that as an plane view. That is nothing but the topper view of the object is being represented with respect to that projection. So this is how orthogonal projections comes into picture. Then, as I told, the brief or the extended part of orthogonal projection is an isometric projection or axonometric projection. So what happens in axonometric projection is it basically shows more than one side of an object. That is, if you want to display both the front as well as back side of that particular object, you can use orthogonal projections, into which you can use isometric projection or axonometric projections, where with the help of which you can display two sides of an object. Check out here orthographic projections. The top view as well as front view of that particular object can be displayed with respect to orthographic projections. Orthographic projection in the sense just one side of the object is being represented. But coming on to axonometric or isometric, you can display any side of the object, that is top view, front view, or the right side view of that particular object also can be displayed. That is, two kinds of sides can be displayed with the help of axonometric projections. Then, what is isometric projections? In isometric projections, basically intersection of plane happens where each coordinate axis in the model coordinate system at an equal distance. That is, if you represent a three-dimension object, a square or a box with respect to x, y, as well as z plane, with the help of isometric projection, as I told, the plane whichever you are defining here, that is XYZ plane, intersect with each other. That is, if there is intersection with these planes only, you will get this three-dimensional object, right? So similarly, you will be displaying that particular object into your V plane with the help of isometric projection. That is, you can check out the same object is being displayed onto the view plane. So this is an advantage of an isometric projection. In this projection, parallelism of lines are preserved, but angles are not preserved. So this is an very important point regarding isometric projection, where as I told, the condition of parallel lines. So these kind of condition is preserved with respect to this isometric projections, but the angle with respect to which the object is being displayed is not considered for the projection. So that was about isometric projection. Then, similar to that of 3D viewing coordinates, we have some coordinates with respect to orthogonal projection as well. So what are these coordinates? We'll check out one by one. With the projection direction parallel to the Z view axis, the transformation equations for an orthogonal projection are trivial. What are the trivial cases we have seen in the previous module? Trivial cases basically tells all the three different planes with respect to that particular object. That is, you can define any of the coordinates with respect to any of the axes, that is x, y, or z axis. So this is an advantage with respect to orthogonal projection, where all the three trivial cases are considered here. Check out the second point. For any position x, y, z in that kind of coordinates, that is, which coordinates? Viewing coordinates. As in the given figure, the projection coordinates are, you are considering one point P with respect to which you will be displaying the viewing coordinates. So suppose this is an view plane. I have defined 2 points here with the help of which projection is happening with respect to all the three planes, that is x, y, as well as Z plane. If suppose I am drawing a point here with respect to XY plane, which comes under the coordinates XYZ, so how this particular point can be defined as with respect to the projection coordinates is, I can define that point. I will take just the product of the point with respect to X plane as well as Y plane, and then define it with respect to each coordinates, that is X and Y coordinates, that is xp. With respect to point P, the x coordinate can be defined as x. Yp, the y coordinate with respect to point P can be defined as y-axis. So this is how the orthogonal projection coordinates with respect to position xyz works. Then in OpenGL, we said something called as clipping window. We know what is a clipping window with respect to 3 dimension by choosing 2D coordinate positions for its lower as well as upper right corners. That is, coming on to your software part, what is a clipping window? I can tell whatever the object is being clipped, wherever it is being displayed. So such part is called as clipping window. If you want to perform clipping window for 3 dimension, basically the basics of 2 dimension should be done, where the coordinate positions are towards the lower left as well as upper right corners. Then check out how that particular clipping window with respect to orthogonal projection is being done with respect to 3D viewing. The clipping window is positioned on the view plane with its edges parallel to x and y view with respect to this particular diagram. Suppose these are the coordinates with respect to x, y as well as z with respect to the view plane. So this is the view plane here. This is the clipping window with respect to 2 points. What is the minimum as well as maximum part of that particular clipping window is xw minimum, yw minimum, xw maximum, and yw maximum. So this is how the clipping window can be displayed for 3D viewing. Then, with respect to orthogonal projections, there is a terminology called as view volume. So, what is this orthogonal projection view volume is? Basically, I can call these two are the edges with respect to the clipping window, which basically specifies x and y elements of the scene which can be displayed. With respect to these 2 points, the limits of x and y are being set so that it will basically so that points are used to display the region of the clipping part. I can tell these 2 points specify the region of the clipping part with respect to which the clipping part is being displayed onto the view plane. So these limits, that is xy limits, are used to form the top, bottom, and 2 sides of a clipping region, which is also called as view volume. That is, whatever the clipping region, that is this clipping window is being displayed, it is dependent on these 2 limits, that is x and y limits with respect to minimum as well as maximum values. So these kind of points or the views which are being displayed are basically used to form the top view, bottom view, or the sides of view with the help of that particular region, which this part whatever we are using is actually called as orthogonal projection view volume. Then there is some condition with respect to the clipping window. If you want to consider, whatever the projection lines are perpendicular to the view plane, these 4 boundaries are the planes that are also perpendicular to the view plane. This basically tells how the lines with respect to the projections are represented. That is nothing but those lines which are being projected to the object are basically perpendicular to the view plane. That is, whatever the view plane you are representing with respect to the clipping window, it should follow with respect to the edges so that it can pass through that particular plane. So this is one condition with respect to projection. Then, with respect to orthogonal projection view, we also consider some planes which are far from the clipping window, near to the clipping plane, and so on. So, whatever the lines which are perpendicular to the projection plane, such kind of planes are basically called as near far clipping planes or front back clipping planes. That is, the lines which are perpendicular to the plane, whatever the plane is represented, such type of plane is called as near far clipping plane. Then, when the near and far planes are specified, we obtain a specified orthogonal view volume. So this we studied in the previous slide as well. Check out the diagrammatic representation of the view volume. If suppose this is the clipping window, with respect to the orthogonal projection, I can produce a view volume. That is, this is a, with the help of this projection, a view volume is being produced. Then I can define which is the nearest plane as well as the farthest plane. That is, the front face of that particular orthogonal projection is the near plane. The back face of that particular orthogonal projection is the far plane. I can define it as. So where these kind of projection is being represented, it is represented in all the three axes, that is x, y, z, with respect to different viewing planes. So this you need to remember what are the near as well as far clipping planes. Then coming on to your programming part, we consider GL ortho, right, in the program. So what does this basically specifies? As you have parameters to it. One is left, right, bottom, top, near as well as far. So this is how the representation is done. That is, what does this left tells? It basically tells the coordinates for the left clipping plane. Whatever right tells, it basically tells the right vertical clipping plane. Bottom is horizontal, top is the horizontal clipping planes with respect to top clipping plane. Then near and far, whatever we studied in this. If suppose this is the orthogonal projection which you got with respect to the clipping window, which is the front face of the object, I can call it as a near plane and the far plane. That is with respect to the object you define in this parameters. Then we have normalization as well. That is normalization transformation for orthogonal projection. That is with respect to the points. As I told, we have some points which to be specified so that a whole object can be shown to you. That is with respect to 2 points, x minimum as well as x maximum, with respect to the 3 types of projections. One is orthogonal projection view plane, with the help of which you can define the normalized view volume. How the normalized view volume is done? First, x, y as well as z plane is being defined, with respect to which the consideration of the point is done. Simultaneously, the mathematical representation with respect to matrices is done, where each and every object's x maximum as well as x minimum is being taken, so that the diagonal of the matrix is matched with each other. That was all about orthogonal projection. So what is orthogonal projection? It is one of the subpart of the parallel projection, in which all the lines are parallel but are represented in the orthographic part. So another type of projection, we saw we want to study 2 types of projection, right? We studied what is parallel projection. Now we have to study what is perspective projection. So what is perspective projection? In parallel projection, as I told, the angle is not much considered with respect to projection part. But in perspective projection, there is a term called distance. So this distance matters a lot in perspective projection. That is, in perspective projection, the distance from the center of projection to project plane is finite, and the size of the object varies with respect to the distance. As I told, the distance matters a lot in perspective projection. The distance is the distance from the center of projection to the project plane is finite. That is, if suppose this is the point of center, that is center of point which is being defined. If I want to consider one point P, I can tell this is the projection plane with respect to the point is projected. But there is something called as distance between this a point as well as this point. So that is called as a perspective projection, where the distance keeps on varying there. The distance and angles are not preserved, and parallel lines do not remain parallel. That is one condition in perspective. Instead, they all converge at a single point called center of projection or projection reference point. In the second example, they have given center of projection in the red shade. This is the red shade. Suppose what happens in perspective projection is, whatever the lines you draw from any plane, so that that points come and meet at a point called as center of projection. At that point, I can call there is a perspective projection happening towards the view plane. So this is how perspective projection comes into picture, where you consider a point where all your points which are being defined from different lines are being submerged there. So that is center of projection. In perspective projection, as I told, the proportions doesn't matter here. It just matters what is the point where the lines are being displayed. Check out the points. Unlike a parallel projection, a perspective projection does not preserve relative proportions of the object. It does not tell you to preserve or consider the projections with respect to that particular object. That is, the angle of that particular object is not preserved simultaneously. What is an example of perspective projection? Photographic lenses and the human eye. Human eye is the best example of a perspective projection. Take an example of human eye. If suppose this is an image you want to see here, what happens here? It basically your human eye calculates the distance as well to which some human eye can see, some human eye cannot see with respect to that particular distance. It depends. It varies on the sight of the human being. Check out, if you want to just check out this image, whatever the important parts of that particular image is being seen by the human. I can tell the face is very important part in that particular image, so that particular object is being visible to an human eye with respect to different dimensions, with respect to different viewing distance, object distance, and the important concept image size. So it depends on all the parameters with respect to that particular image. So that is an example of perspective projection. When an observer sees a scene in day-to-day life, the far away objects look smaller relative to closer objects. This is an terminology where we all know that if the objects are far away from the human eye, it looks smaller. If it is very much nearer to your eyes, it looks bigger, right? So that is the concept of human eye. This projection properties can provide a knowledge about depth. This basically, whatever the point which is being specified here, it basically tells you the depth of an human eye or the depth of that particular image as well. So we can employ some projection for drawing 3D scenarios with respect to the depth of the object as well as the depth of the observer. Some properties can be observed with respect to three-dimension scenes. Then, in perspective projection, there are two important characteristics you need to remember. One is perspective foreshortening as well as vanishing points. So, what is this perspective foreshortening and vanishing point? With the help of foreshortening, lengths as well as objects seem smaller from the center of projection. This is an advantage of perspective projection. If you are using foreshortening of perspective projection, what it does is it basically shortens the length as well as the object size, so that the object is being seen smaller by the user with the help of what? Center of projection. Then the more an artist increases the distance from the projection center, the small will the appearance of the object. That is, it basically depends on the viewer, how he basically varies the distance of an object from the COP, that is center of projection. Then the appearance of that particular object varies with respect to that particular distance. As I told, in perspective projection, distance matters a lot here. So in perspective foreshortening also, distance keeps an important role. Then in vanishing point, how can I consider vanishing point is, it is actually called as an side effect of an perspective projection. That is, as to take an example of some medicine, if I can tell, there might be some side effects of that medicine as well, right? Similarly, with respect to perspective projection, vanishing point is the side effect. So what is vanishing point? Basically, vanishing points, parallel lines that are not parallel to the viewing plane gives you the vanishing point. That is, some of the lines can be considered in the viewing plane where that lines are not parallel to that particular projection. Take an example of this. If you take an example of a railway track, for an example, if you stand at the center of the railway track, you can check out the track looks goes on becoming smaller, right, towards till your eyesight reaches there. So this is one of an example of perspective projection. You can check out the distance between the lines keeps on decreasing, and the size of the lines is actually not parallel to the initial stage of the line. So this is an example of perspective projection. Simultaneously, with respect to vanishing point. So what is the vanishing point? If suppose this is a line which is being projected onto the view plane with respect to different points, if I note that the intersection of point here is a vanishing point, what happens here is these lines are basically not parallel to the lines which are being displayed at the initial stages. So that is how vanishing point comes into consideration with respect to different view planes. Then there is some condition with respect to perspective projection. Based on the number of vanishing points, the perspective projection is of three types. These perspective projection is divided into subparts only based on the number of vanishing points. That is, one is single point perspective projection, double point perspective projection, and the third is triple point perspective projection, which is actually called as 1 point, 2 point, as well as 3 point projection as well. Let's see in a bit detail about the types of perspective projection. First is 1 point. What happens in 1 point? In single point perspective projection, there will be only one vanishing point. That is an example of this. I can call this as an 1 point projection, where vanishing point is 1 here defined with respect to perspective projection. In this example, check out this example. I cannot tell the number of vanishing points here, right? I can just tell how the points are being vanishing with respect to the human sight. That is the 1 point where I can tell there is only one vanishing point with respect to that particular plane. An example of 1 point: when the cube is projected to a view plane that intersect only z axis, a single vanishing point is in the z direction. That is, if I consider this is a cube which is being represented for an 1 point perspective projection with respect to three different planes, that is x, y, z. How perspective projection happens here is it will take the back part of that particular object and points at 1 point, that is where all the points are intersecting, all the projection lines are intersecting at 1 point. I can call that point as vanishing point, which is being defined in the view plane. Then similarly, 2 points, which basically consist of a couple of vanishing points, that is 2 points with respect to x and y plane. The first vanishing point will be in the direction of x, the second vanishing point will be in the direction of y. So this is how 2 point vanishing happens. And check out here, what happened in 1 point. Basically, with respect to the object, there was only single vanishing point, but check out in this example there are two vanishing points with respect to different axes, that is x as well as z here, or I can tell x as well as y vanishing point, that is 2 point perspective projections. When the cube is projected to a view plane that intersect both the z as well as x axes, which consist of two vanishing points, that is production of two vanishing point happens there. Then check out, can someone tell how many vanishing points are being there for this examples? I will tell. If suppose I consider a cube with respect to that particular object, I can define 3 vanishing points with respect to this object. And for the second object, 2 vanishing points. For the third object, 1 vanishing point. It depends how the object is being displayed. Check out here. I can see almost all the sides of the object in this part, right? So I can tell there is 3 point perspective. In this, I can't see the back face of the part of the object. So I can tell this as, I can represent in the form of 2 point, and the third one as 1 point, because just the single phase of the area is being seen. So this is how vanishing points works. Looks quite simpler as well with respect to perspective projection. Then With respect to perspective projections, there are some transformation coordinates as well, which basically depends on axes only. So basically, if I consider this as a view plane, if these are the points passing to that particular view plane, if I consider a single point P, which consists of three planes, that is X, Y, as well as Z, with respect to that point, how perspective projection happens is there is some transformation coordinates included here, with the help of which you can project some points with respect to the X, Y, as well as Z plane. What does this figure indicates? The projection path of the spatial position. That is, this is the projection path which has been happening here with respect to X, Y, Z to a general projection reference point at XPRP, YPRP, as well as ZPRP, which basically tells the projection path with respect to some reference point. With the help of what? This acts an interface here, that is the view plane. Then simultaneous the representation of transformation coordinates with respect to X, Y, as well as Z axes. Then check out how we get this XP as well as YP value. This basically depends on these values which we have represented. First point is being evaluated with respect to X and Y coordinates, but check out the next point which is being evaluated with respect to the same is a complement of X, Y, as well as Z, which basically tells you are subtracting with respect to X, Y, as well as Z plane with respect to this coordinate projections, that is the projection points of this. So how you will calculate u? What basically u tells us it is nothing but the axis with respect to which the position is being represented. U basically tells you the position of the object. It basically happens with respect to the z plane itself. As I told, the type of projection depends on the axes, that is XYZ axis, depending on the plane which has been represented. So this is how representation is done. Then there is something called as view volume as well, that is perspective projection view volume, as similar to that of parallel projections. The perspective projection view volume is basically often referred as the pyramid of vision because it consists of approximations with respect to cone of vision of our eyes or camera. As I told, the viewing plane is dependent on the viewer. It should view with respect to some projection points. Check out the reference point here. There is an initial point. If I consider this looks like a pyramid, right, with the help of which a view plane is being generated with respect to different planes. Simultaneously, you check out here, there are front plane, back plane, as well as view volume as well with respect to perspective projection. Part with respect to perspective projection. As we discussed this, we have a function called as GL Frustum, which basically gives you the perspective projection metrics with respect to the parameters, that is x minimum, x maximum, y minimum, y minimum, and near far part, that is with respect to the object. Check out this an example. This is an perspective projection with the help of GL Frustum. If you want to perform this as an perspective projection of this particular object with the viewer, this is how, if you're using this functionality here, with the help of GL Frustum, all the left part, top part, bottom part, near part, and the right part will be displayed with respect to that particular object. Then matrix representation with respect to homogeneous coordinates. How the matrix is being represented is, first you will calculate the coordinates with respect to the perspective projection, which is being given by PH, which is given by matrix with respect to the perspective, which is given as a product of that particular point P, where PH is the column matrix representation of homogeneous point, which parameters are given here, where P is the column matrix represented by the coordinate positions x, y, z, as well as 1. So you can check here, the perspective projection matrix is a combination of all the three axes x, y, as well as z. So you can check each and every values is being represented with respect to taking each and every coordinate values. Then once the matrix part is done, what we have to do, we have to process, that is another process can be applied, such as normalization transformation, where I can perform clipping as well with the help of all the three x, y as well as z coordinates. So that was about basic about perspective projection. Now there is some two types with respect to frustum as well, where frustum comes in your programmatic part. What happens in two types of frustums is, the first is symmetric perspective projection frustum, and the second is oblique perspective projection frustum. These two types are being mentioned in your syllabus, with the help of which you can give a multi-view for that particular projection type. In symmetric perspective projection frustum, what happens? It basically draws a central line for a perspective projection. That is, if this is the perspective projection frustum happening, so this is the center line drawn with the help of that frustum. What it basically tells is, it basically tells the projection reference point to the center of that particular clipping area. If I consider this as a clipping window with respect to the clipping plane, the area which is being divided with respect to the frustum center line gives you the center of projection. So with the help of this center line, a clipping window can be performed with respect to the nearest area. If this center line is perpendicular to the view plane, we have a symmetric frustum. So this is how symmetric frustum can be defined. Whatever the line is being drawn with the help of frustum center line, if this particular line is perpendicular to the view plane, what is the view plane? This clipping window is the view plane. I can see this is perpendicular to the view plane. So at this stage, I can tell this is an symmetric frustum happening here. Then simultaneously with respect to symmetric frustum, there is some intersection happening here with respect to the clipping plane as well as the view plane. At that point, there is some location. The coordinate location is being defined with respect to x perspective point, y perspective point, as well as z perspective point. How can we express these points with respect to the corner positions of window dimensions? What happens in window dimension is, if suppose this is a clipping window you have defined here, as we know, we should define some dimensions with respect to that particular window, right? It basically depends on the type of axes you are defining such kind of windows. So this is how symmetric different frustums. So these are the minimum as well as maximum values which are being defined with respect to the clipping window positions. It basically depends on the width of that particular area. Then the another type, that is oblique perspective projection frustum. What happens in oblique perspective projection is, as it also consists of a center line which is being drawn with the help of frustum, but if that particular line will not be perpendicular to the window plane, that is view plane. If this line, that is frustum center line, which is being projected, if it is not perpendicular to the view plane or the clipping window, I can call at that time it is an oblique perspective projection happening. So this is simultaneously a representation of oblique perspective projection, where it consists of some view planes, where conversion of a symmetric frustum by applying sharing transformation. What is sharing? What is share? Share is nothing but reduction in the size of the object, or increment in the size of the object. So the representation of oblique perspective projections with the help of matrix is given here, where all the diagonals is represented as identity matrix with respect to two axes of share, sh zx as well as sh zy, which can be calculated with this formula. Then the representation of share transformations with respect to oblique projection is given above. Then this is how the final oblique perspective projection matrix is being given, where the product of both the matrices with respect to share as well as perspective matrix is done. Once this both the product of this particular matrix is done, you will get the resultant matrix as this.